So we're going to do a little bonus video on formal charge. This is not anything we're going to be assessed over, but the question always comes up at some point, so I want to go ahead and tackle it. So for instance, if we were to look at a structure for a SO3 molecule, one of the pieces of guidance that we used to figure out these structures was that the atom that can form the most number of bonds typically finds itself in the center of the molecule, but sulfur and oxygen both have the same number of valence electrons, so they both tend to form the same number of bonds. And so there are several different structures we can look at, but let's put two clear, valid Lewis structures for this, and that is the one on the left there, and then we could put them all in a line here on the right, and those would be two valid structures. We have 8 valence electrons on everything. We have the correct total number of electrons, so these would be valid structures. Determining which one of these is the more likely structure is something that formal charge is useful for. And then, of course, we can always verify this with certain analytical methods. But the formal charge for any atom in a molecule is equal to, so Fc, the formal charge, is equal to the number of valence electrons of that element minus the sum of its unbonded electrons and half its bonded electrons. So essentially, in that subtraction term, it gets to claim all of its unbonded electrons and one of the electrons from each of its bonds. And in terms of molecules, the formal charge on a molecule is the sum of the formal charges on all of the atoms. So let's see if we can apply formal charges to these two structures. Let's start with the oxygen on the top left of the left structure. Oxygens have 6 valence electrons. There are 6 unbonded pairs of electrons, or 6 unbonded electrons, 3 pairs. So if you subtract all 6 of those, you end up at 0, and then it also gets to claim one of the electrons in the bonded pair with sulfur, so you subtract one more, giving you a -1 formal charge on that oxygen. Of course, the one on the bottom is going to be -1 for the same reason. Sulfur has 6 valence electrons and only gets to subtract 4 as it claims 1 electron in each bond. So you're going to get a +2 formal charge on sulfur. And then the oxygen, which has 6 valence electrons, will take 4 away from the unbonded pairs, and then 2 more as it claims 1 electron in each of the bonds, and so you get a formal charge of 0. Formal charge on this molecule then is going to be 0. +2 is canceled out by the 2 1 minuses, and so in that respect, we're in pretty good shape. We go over here, the first oxygen on that molecule is going to have a -1 formal charge for the same reason as the oxygens with only 1 bond on the left. The sulfur, if we run its formal charge, it's going to end up at 0. Oxygen up here is going to be +1. And then the final oxygen with the double bond there is going to be 0. Again, total formal charge on that molecule, also 0. So in order, we kind of go through a series of things to determine which one of these things we think is going to be the most likely. And the first thing we're going to look at is formal charge of the molecule being as close to 0 as possible, where both of them are 0, so we're in good shape there. Second thing we're going to look at is the location of the formal charges, and we're going to look to see that negative formal charges are on the most electronegative element. So oxygen being more electronegative than sulfur, we confirm that in the molecule on the left. The molecule on the right, though, we have a positive charge on the oxygen and a 0 on the sulfur. And so we would expect the positive formal charge to be on the least electronegative element, and the oxygens to have either negatives or a 0. And so that's going to tell us that the molecule on the left is the more likely structure here. And again, this can, of course, be confirmed with analytical methods to look at locations of atoms. If 1 and 2 are the same in both molecules, then we go and look to see the least number of molecules with formal charge, or least number of atoms with formal charge would also help guide us to which one we think is the most likely structure. So let's see if we can't do a little practice here. So see if you can write valid structures for POCl3 and SOCl3 to kind of give you a hint there. The chlorines are going to have to go on the outside of the structure. They can only form 1 bond. So you can look at attaching those chlorines The phosphorus and the oxygen are obviously going to be bonded together, so where are all the different places you can attach the chlorines? Same thing with the SOCl3. The sulfur and oxygen are going to have to be bonded together, and then what are all the places we can attach the chlorines? And so we'll look at structures there, try to find formal charges and see which one is the most likely. You should pause the video and take a stab at it. So here are the two structures for these two molecules. And then we can go through and attach some formal charges here. Your chlorines, which have 7 valence electrons, and then we subtract 6 for the unbonded pairs and 1 for the bonded pairs, are going to get us to a 0 formal charge on all the chlorines. Oxygen is going to carry a -1. The phosphorus is going to carry a +1. So we have a 0 formal charge there. And we have a negative formal charge on the most electronegative element. We'll come back to this molecule in a second. Let's bounce over here to the SOCl2 and throw some formal charges out there. And again, when we have the chlorines on the sulfur instead of the oxygens, we end up with our negative formal charge on the oxygen, which is the more electronegative element. Of course, what we're actually going to find with this structure is that sulfur is going to expand its octet, like we mentioned before. It's going to move some electrons into some d orbitals, because if it can form a double bond with that oxygen, now you got a formal charge on of 0 on everything. And so this molecule actually tends to form that structure with the double bonded sulfur. Again, we're mostly going to deal with octets, and we're not going to deal with expanded and limited octets in here. All of our structures that I'm going to have you guys perform are gonna meet the octet rule. As a side note, that POCl3 will also push a double bond between the oxygen and the phosphorus, but it tends to hybridize between those two, where sometimes there'll be a double bond, sometimes there'll be a single bond. And orbital hybridization, or not orbital hybridization, resonance structures and resonance hybrids are what we're going to look at in the next video.